So now that we spent a great deal of time actually talking about and developing this limit equation that we can use to help us figure out the derivative of a function, we're actually just going to apply this limit to different types of functions to figure out what is the derivative. Okay, what is the slope of the tangent line at any point on the specific graph. So at this point, whenever you hear the word derivative, I want you to think slope of tangent line and vice versa. Whenever you hear slope of tangent line, I want you to think derivative. Now we will get to some other phrases throughout the year that we can use to represent the idea of a derivative, especially when we get into particle motion and like velocity and acceleration. There are going to be some other phrases, but for right now, whenever you hear derivative, I want you to think slope of tangent line. So what we're going to try to do is apply this limit equation, okay, this derivative formula, to these two particular examples. So if you take a look at the limit itself, this time we have h approaching 0, so it's no longer an x, and we have this interesting notation f of x plus h. So this x plus h is just representing an input amount or an input value. Just like if you would have f of 3, you would plug in 3 for all the x's. But this notation is telling us to take x plus h and plug it in for all the x's in the equation. Maybe you only have 1, sometimes you'll have 2, maybe you have more. But the idea is we're going to take x plus h and plug it in for every x. So let's take a look at what this limit might look like. So if we take x plus h and plug it in for the x, we'll have something that looks like that. And then the limit notation goes on to tell us that we want to subtract f of x. But notice how f of x just represents the beginning equation that you're starting with. Now we have to be careful and put it in parentheses because just like our equation here has multiple terms, we'll have to distribute that minus operation to both values. And this is all over h. So what we should be able to do from here is kind of simplify and see where things would take us. We can distribute in the 2/3. And then we can also distribute in the minus sign. Now some interesting things might happen. Notice how positive 2/3, negative 2/3, those would go away. And then this should be a minus 3 because we want a minus 3 and a positive 3 to cancel out as well. So it looks like we're just left with 2/3 h over h. And with the h's canceling, it looks like we're just left with 2/3. So we can label our derivative f prime of x equal to 2/3. Now since the h is canceled, we really didn't have any left over to plug in 0, so we're going to be left with 2/3 in the end. So this derivative is representing the slope of the tangent line at any point on this graph of f of x. Okay, so this is the slope at any point. And hopefully it kind of makes sense because notice how the equation we started with is a line, and a line has a constant slope. So at every single point you would have the same rise over run. And notice how the slope we got at any point 2/3 matches the slope of the equation, okay, of 2/3. Now the next one is a quadratic. So this one probably shouldn't have a constant number because if you think about a parabola and you were to plot a point anywhere, okay, notice how the slope values would change. So we should have some, perhaps a variable left over. That way the variable can affect the change depending on which point or which x value we want to use. So let's go ahead and set up our derivative limit. We're going to substitute in x plus h for all the x's, and then we will subtract the original function, and this is all over h. Hopefully you guys are able to write a little smaller than I am with this pen so you can fit it in a little bit better. Now, through movie magic, if you will, if we were to write x plus h twice and go through a FOIL process and then distribute in the 1/2. So I'm going to kind of take this to the final representation, if you will. But if you need to actually go through the steps, go ahead and write them out. So I'm going to FOIL x plus h and then distribute in the 1/2. So we'd have 1/2 x squared plus xh plus 1/2 h squared. So that's just this first part rewritten and simplified. We then can distribute in the -2, and then we can distribute in the minus sign. So very similar to the other example, a lot of terms should cancel out, and we'll see what we're left with. So positive 1/2 x squared, negative 1/2 x squared are gone. Negative 2x, positive 2x, positive 3, negative 3, all those are gone. So we're left with xh plus 1/2 h squared minus 2h all over h. So notice how h is approaching 0, but if we still were to plug in 0 for all the h's, we'd have 0 over 0. So we have a little bit more to do from here. We could factor out an h from the top. So we're left with x plus 1/2 h minus 2. And this is still all over h. So those are gone. And finally, if we substitute in 0 for the remaining h, this term would disappear. So it looks like we're just left with x minus 2. So we can label this as the derivative of our function. So this is representing the slope at any point. And with the variable still in there, it's just representing how the slope would change depending on the point that you actually were interested in using. So unlike a line that has a constant slope, notice how a parabola has a varied slope, okay, depending on the point you want to use. And that kind of makes sense if you actually think about the graphs. So if we take a look at these results a little bit further, we might be able to find another interesting connection here between the derivative we produce and the original equation that we start with. So notice how the derivative for this linear function was constant. Okay, it was just the number 2/3. So the derivative for a line was a constant, and notice how the derivative for a quadratic, okay, this parabola, we started with a parabola, and notice how the derivative is linear. Okay, this is mx plus b, we have an x minus 2. So it looks like we do have a connection here. If a line has a degree of 1, okay, an x to the first, notice how the derivative is constant, meaning it has a degree of 0. There's no x left. And then for the next one, if we start with a quadratic, which is a power of 2, notice how the derivative was linear. Okay, it has a power or a degree of 1. So it seems that we have this pattern here where the derivative is 1 less degree than the original function. So maybe we can say f prime is 1 less degree than f of x. So this is a good pattern for us to realize now, and when we start to get a little bit deeper into these derivatives, it's going to make even more sense. But for now, at least it's a good pattern to be aware of and recognize.